Recording is started. There it is. Okay, so we're going to continue Chapter 8, now in Section 8.5, Applications of Physics. All right, so do you know the concept of work? How to measure work, how much work you do? Under what curve? Area under the curve? Okay. Well, let's define work, how much work you do physically, as force times distance. Okay, technically it's a dot product of a force vector times a displacement vector, but what we're going to say here is it's a component of the force. It's a component of the displacement that works against the force. Okay, so if, say, I drop my book on the ground, boom, and I pick it up, am I doing work? Right? Against what force? Force of gravity. So the work that I'm doing, I'm pulling this thing up vertically. The force of gravity is also pulling down vertically, right? So I am doing work against a certain force. But what if I take that book and I just walk it across the room to give it to you? Am I doing work? I'm taking this book and I'm just walking across the room. Am I doing work with regards to that book? Not technically, because there's no force I'm working against. Unless I'm going really, really fast and there's like air resistance or something, right? But I'm just walking across the room and I got this book. The book isn't going up and down. It's not working against gravity. I'm just moving it horizontally to you. Technically, I'm not doing any work. Okay? So, for example, let's say my book weighs 2 newtons. And I pick it up. I'm picking it up, say, 12 meters. How much work did I do? It's 2 newtons times 12 meters is 24 what? What are the units now? Newton meters, right? Oh, what is that? Well, that's a legal color, I guess. So that's Newton meters, okay? That's in the English system, that's how that works, okay? I mean, not in the metric system. What if it was in the English system? Let's say this book weighs 3 pounds. Now, this is what people don't realize in the English system, that pounds is not a unit of mass. Pounds is a unit of force, okay? Do you know this expression? This is one of Newton's laws of motion, right? Force is proportional to acceleration. What if that force is due to gravity? The acceleration due to gravity. That's your weight, right? Your mass times the acceleration of gravity at that point on Earth or on the moon or whatever, right? So if I said that the book weighs 2 newtons, what's its mass? Because that's a force, right? Weight is a force. Your weight is different on the moon than it is on the Earth, but your mass is the same. So what's your mass? Say you have an object that's 2 newtons in weight, and you're on the Earth. What's your mass? Simply take this and divide our weight. Now I'm just rough figures. 9.8 meters per second, right? Rough figures, 10 meters per second. Divide by 10 to get 0.2 watts. Actually, kilograms. There's MKS and there's CGS. There's 2 metric systems. Did you realize this? If you do all your units based on meters, kilograms, seconds, or all units based on centimeters, grams, or seconds. All right? If I'm talking about 10 meters per second, then I'm talking about kilograms for mass. Okay, so if roughly this is 10, m is about 0.2 kilograms. Okay? But look at that here. What about here in the English system? What the heck is the unit of mass in the English system? In the metric system, it's kilograms or grams, you know, that kind of thing, right? It's slugs. You've heard of this? Okay, so if I do this again, I say your weight is 3 pounds, What's G? I'm not in the metric system now. G is not 9.8 meters per second per second. G is now what? 32 feet per second, roughly. Rough figures, say 30. So if G is about 30, how do you get M? Divide 30 into 3 and you get 0.1. So now my mass is 0.1 slugs, believe it or not. Have you ever heard of that unit? Slug, not as in a snail without a shell. Slug as in a pellet from a musket. In old England, they had muskets with pellets. When you shoot somebody, all these pellets go flying out. The mass of one pellet was a slug. Okay, that's where it comes from. Those little pellets were called slugs, too. Bullets are sometimes called slugs. Right? Yeah. All right, that's the idea. All right, so just realize units. Be careful with the units, okay? All right, so say the book weighs 3 pounds, and I'm lifting it 4 feet off the ground. What's the work I did? It's force times distance, right? The distance that you're working against the force. I'm going vertically, so I'm working against gravity. So it's going to be force is 3 pounds times distance is 4 feet. So what do you get now? 12 watts. Foot-pounds. All right, you ever hear of a foot-pound? Okay. So in the English system, we're talking about foot-pounds for a unit of work. And you can talk about foot-pounds per second or foot-pounds per hour as a unit of power. Here we can talk about Newton meters for work in the English, in the metric system. And Newton meters per second for power. Newton meters is also known as a joule. And Newton meters per second or joules per second is known as a watt. You ever hear of watts? Right? Okay. So be careful with the units. The problem is, though, here it's nice and easy to figure out the work you did because the force is a constant. What if it's not? That's what we're going to talk about. Okay? You ever hear of Hooke's law? Here's Hooke's law. Let's say you have a spring. And its natural length is whatever it is. It has a certain natural length. Let's say that's what it is. Let's say we call y equals 0 where it lands. Now if I extend it or compress it, the spring will work against that. Have you ever seen one of those like big, huge, fat springs like in a suspension in a car? And can you imagine compressing it? You ever try playing with those things? It's a nice, thick spring. You can't compress it by hand, right? The car can do it because it weighs 2 tons. But I can't do it. Big, huge, fat springs have a huge spring constant. And little skinny little springs like in a pen, a ballpoint pen, right? That you click, the little springs in there have very little spring constants. And according to Hooke, the force that the spring exerts against expanding it or compressing it is the force is directly proportional to the distance you compress it. Well, in this case, it's y. Let's say delta y. So if y is where you are, the length of the spring, right? Delta y is how much you've compressed it. Okay, so say you moved it up an inch or 2 inches or something, that's your delta y. And there's some constant k of proportionality that represents how stiff the spring is. And this force is working against you, so we're going to call it negative. If k is a positive number, we're going to say there's a negative force working against you. That's Hooke's law. Okay? So, let's see, what can I do with Hooke's law?
Force one way or the other required?
No, as long as the spring is not deformed, no, actually. You can actually destroy the spring if you pull it too long and it doesn't go back to its natural length. You've ruined the spring. It's no longer a spring. It doesn't have a spring constant anymore. But if you don't deform it, the spring constant is the same both ways. Yeah. So compressing it or extending it, I don't know what you call it. Stretching it, and shrinking it. How about that? Okay. The same force applies. It works against you, right? If you pull it, it gets harder and harder and harder to pull as y gets bigger. Delta y gets bigger. If you smush it, if you compress it, As delta y gets bigger, 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 it's getting harder and harder and harder to compress it. Right? So as delta y gets bigger, the force is stronger. Right? All right, so let's say, how am I going to say this? Let's say they give you a spring whose spring constant is K equals, I don't know, what's a good spring constant? 8 newtons per meter. Does that make sense? If the spring constant is in newtons per meter and delta y is in meters, the meters cancel and you get newtons for force, right? That makes sense. Okay. So, what is the work what am I trying to calculate? Force, right. What is the work done in compressing this spring with that spring constant 0.1 meters, let's say? So I'm going to compress it a delta y of 0.1 meters. Now remember, the work done is a force times distance, right? Okay. If the force is Did I write this wrong? Hang on. Where's the statement of focus law? Yeah, I might have misspoken this. Hang on. Do I want to do that? All right. Let's do it this way. Force times distance, right? Now the distance that I'm moving here is delta y. But the force is also proportional to how much you're moving it. So I'm going to say that the force is negative ky. I wrote this wrong. I should just say y. How long it is. Okay? Delta y is how much you're moving, compressing it, but y is the force at that point. Right? Y gives you the force at that point. So if I'm saying that the amount of work done to move this a certain delta y is the force times that distance, it's ky, negative ky times the distance. That's your Riemann statement. How much work is done? How do you make that an integral? We're given that k is 8, by the way. It's the integral of what? How do you convert this to an integral? This is just a Riemann statement. K is from 0 to 0.1 they wanted? Okay, fine. And K is 8? Okay. So it's 8y dy. Now the fact that it's negative, that's because it's working against you. But I'm not really worried about whether it's positive or negative. I just want to know how much work I'm doing. So I'm not going to worry about whether it's negative in this case. Just the absolute value. All right, so what's the antiderivative? 8y squared over 2, in other words, 4y squared. Evaluate it from 0 to 0.1. Okay. So you're going to get 4y squared, 4 times 1 squared, 0.1 squared, minus 4 times 0 squared. But 0.1 squared is, or 1/10 squared is, 100th. So you get 400ths, 0.04. Now don't forget that this is Newton meters, K is Newton meters, and this is meters, right? So you got this in, wait, I wrote this, I'm losing it, Ky delta y. Okay, this is in Newton meters, this is in newtons per meter, this is in meters, and this is in meters. What's newtons per meter times meter? What's newtons per meters times meters? Newtons. And what's newtons times meters but Newton meters? So this is the unit of work, Newton meters. Okay. All right, Newton meters are joules. It's also known as joules. All right, so there's an example where you need integration to figure out the total work done, because the force itself is varying. For different values of y, if y is big, the force is big. If y is small, the force is small. The force is changing. So you have to add up all the little forces for each little delta y, for each little piece of this motion that you're doing. Okay? There's an example, another example of where you need a Riemann statement. Okay, how about, let's see, how about this one? Okay, how about this? Let's say I have a tank, an oil tank, in the shape of a cylinder. Okay? The cylinder is 25 meters wide, and it's 20 meters deep, and it might be like sunken into the ground or something, whatever. And right now, it's filled only 10 meters worth of oil. Okay? My question is, how much work do you have to do to pump out all the oil to the surface, to the top of the tank? Forget about if you have to take it from there somewhere else, that's something else. But from where it is to the top of the tank, how do you figure out the work done? Well, I can talk about volume, okay, in cubic meters. And I can talk about density. Let me give you the density of the oil. The density of the oil is 800 kilograms per cubic meter. The density of the oil is 800 kilograms per every cubic meter. Okay. Okay. So let's do it methodically. Ready? Let's do this. Let's say that I have. How do you find the volume of a cone? We've done this. You make this little cylindrical shape here, or disc, if you like. Okay. Can you give me a delta V, a Riemann statement for the volume of this mess? Wait, I'm missing something here. Hang on. Missing something. How's that Newton's? Oh, right. Okay, yeah. Okay, I'm good. Okay. Okay, so what's the volume of, let's just do the volume of the cylinder. Then we're going to do the force exerted by the oil. Now, I'm drawing this little cylinder here, but I probably should have drawn it here because I'm talking about oil, a piece of oil. Okay? So pretend I'm drawing it here so it's easier to see what I'm doing, but technically it's a slice of the oil. I want to pump a slice of oil, one slice at a time, add them all up, right? So what's your volume? How do you do that? Well, the face is a circle, so you do pi r squared. If I call this whole diameter x, it's x over 2, exactly. All right, so it's pi r squared, but that's x over 2 squared. And then what's the thickness? Delta y. Okay. Now let's play that game. How to get x in terms of y instead of x here so it can integrate? Well, what's the relationship? The base of this triangle is to the base of that triangle, as the height of this triangle is to the height of that triangle, right? So, where did I put this thing? How did I do this? Yeah. All right, so the height, so up to here, let's say this is a y value, how high the cylinder is from the ground, let's say. All right, so the height of this triangle is y. The height of this whole thing is 20. The base of this triangle is x. The base of this whole thing is 25. So what's the relationship between x and y? X is to 25 as y is to 20. All right, let's write that. X is to 25 as y is to 20. I want to get X alone so I can replace it in terms of Y. How do you get X alone? 25/20ths of Y. By the way, 25/20ths reduces by 5 to what? 5/4 of Y? Okay. So now my Riemann statement for delta V is pi x, which is this, divided by 2. What is 5/4 divided by 2? 5/8. And I want to do 5/8 of pi of y squared delta y. Okay? I can simplify it further later. Let's just leave it at that. That's the volume of a cylinder. Pretend it's in the oil, okay? That's the volume of a slice of oil. What's the force exerted by that slice? What's the force exerted by that slice? Now notice what I'm doing. I'm pumping this thing vertically. So the force I'm working against is what? Gravity. So what I really want is the weight of that slice. This slice is in what units? What units? Y is in meters, right? Delta Y is in meters, Y is in meters. I'm squaring it. What is this whole thing? Cubic meters, right? What I want to end up with is newtons. What if I take that number of cubic meters and I multiply it by the density of the oil? Let's say the oil is uniformly dense, 800 kilograms per cubic meter. If I take cubic meters and I multiply it by kilograms per cubic meters, what do you get? Kilograms. Okay, so what if I do pi times the density times this stuff? Is that newtons? I wanted newtons, right? That the unit of force here is newtons because I'm talking about meters and kilograms. Is that newtons? No, that's what? That's kilograms, right? Okay, so kilograms, that's your mass. Remember what Newton said. Force is mass times F equals m A. Here A is gravity, so m g. So I don't multiply just by the density, because if I take kilograms per cubic meter times cubic meter, I get kilograms. If I multiply that now by g, meters per second, I get newtons. All right? If you take a look at the units of force, is the units of mass times the units of acceleration. The units of force is newtons, is mass, which is kilograms, times meters per second. So newtons is shorthand for kilogram meters per second. That's what I have here. The density, which is in kilograms per cubic meters, times this volume, which is in cubic meters, gives me kilograms. Times the acceleration due to gravity, g, is in meters per second. So this is newtons. Okay, great. But I wanted work. And how do you get work? Force times what? The distance that you have to move against that force. All right, so what's your statement for delta W? How much work? See, delta V is how much volume in one slice of oil. Delta F is the force that slice is exerting due to gravity, the weight. Delta W is that force times how far do you have to transport it. How far does this slice have to go to get to the top? If it's Y off the ground, and it's got to get to 20, how far does it have to be transported? 20 minus Y. So if I take this whole humongous mess, and multiply it by 20 minus Y, I get a Riemann statement for the total amount of work done to pump that oil out. How do you get the total work then? How do you get W out of that? You convert this Riemann statement, which is the work done on just one slice of oil, to an integral, right? Which is adding up the work on all the slices of oil. So you rewrite that as an integral from what to what? 0 to 10 though, because it's not full. If it was full, I'd go from 0 to 20 because I got cylindrical slices of oil all the way up from 0 to 20, right? But in this case, remember the cylinder? I drew it up here to make it easy to see. It's in here. It's only from 0 to what? 10. So I'm doing from 0 to 10. That's how much I'm pumping. And each slice is being pumped 20 minus y out. So the distance that is being pumped is here, but how much I'm pumping is here. Okay? Now, this is just a constant. I could leave it out or leave it in. I don't care. Put it here, I guess. Okay, question?
I think I'm sure you want this right. I expect to think it's 20, but that gives a different answer.
Well, 10 to 20 is if it's full, and you got to pump out everything, right? But it's not full. It's only from 0 to 10 that you're doing work. Right? And remember, again, the idea is that this slice is in here. So I'm describing all the slices in here from 0 to 10. Okay. All right, so now let's work this out and see how many Newton meters or joules of work we have to do. All right, so delta was 800. G, what's G? 9.8 meters per second. Pi is pi, blah, blah, blah. That's, we got everything, right? So it's 800 times 9.8 times pi can come out. Let's write that as out over here. W is the density, 800 kilograms per cubic meter, times 9.8 meters per second, times pi, the integral from 0 to 10 of, what the heck was it now? 5y over 8 squared times 20 minus y. 5y over 8 squared, well, isn't that 25y squared over 64 times 20 minus y dy. That's the integral you have to do to figure out the total amount of work done to pump all the oil out. Okay? So, the 25/64 can come out too if you want. If you like round figures, you could maybe think of this as 10, but that'll be a bad estimate, really. How do you integrate this stuff? Forget about the 25/64 stuff, you can pull that out. How do you integrate y squared 20 times 20 minus y dy? How would you integrate that? Is that a u sub? What is that? What do you do? Hey, who's u then? 20 minus y would be an inner function? Yeah. That's not going to give you y squared dy, is it? du? It's not going to give you, no. So, you could do by parts, but I think it's easier here to simply distribute the y squared. Okay, so what I got here is 25/64 of 800 times 9.8 times pi, the integral from 0 to 10 of 20y squared minus y cubed, isn't it? And that antiderivative is easy to do. What is it? 20y cubed over 3 minus y to the 4th over 4. 25/64 times 800. I guess I could reduce here 8/64, right? 1/8, whatever. Times 9.8 pi. And the antiderivative is 20y cubed over 3 minus y to the 4th over 4, evaluated from 0 to 10. 0 is easy, just drops out. Just plug in 10. Okay. So you get 25/64 of 800 times 9.8 pi times, now let's see, 10 cubed is 1,000 times 20 is 20,000 thirds minus 10 to the 4th is 10,000 divided by 4, and then minus 0, right, if you plug in 0. So, you know, you want to finish that off? What's the common denominator? 12. So multiply top and bottom by 4, you get 80,000. Top and bottom by 3, you get 30,000. 80,000 minus 30,000 is 50,000 twelfths. So you end up with 25/64 times 800 times 9.8 pi times 50,000 twelfths, and you can reduce and stuff. That's good enough. What are the units? Newton meters or joules, yeah. Newton meters or joules, if you like. Now, if you actually pump this out with a pump, it's got a rating. It's going to say how many Newton meters or joules per second or per hour it can do. So if you get, I don't know, a pump that's like 1 horsepower, I think 1 horsepower is 650 Newton meters per second or hours. Oh God, I forgot. I have to look that up. I have a feeling it's not seconds. Yeah. I think a horsepower can be defined as 650 Newton meters per hour, actually. So you can figure out how long it takes to pump this out by using power. Power is how much work you do per unit time, right? So if you have a 1 horsepower pump or engine that can pump this oil out at a rate of 650 Newton meters per hour, just divide this by 650 Newton meters per hour, you're going to figure out how many hours it takes. But nobody uses a 1 horsepower pump. What if it was a 10 horsepower? It would take a tenth as long. What if it was 100 horsepower? It would be 100 times 100 times faster, and so forth. All right. So the issue of work and power very closely related. But this is just work. Okay. Questions? Okay. Let's try that again. Let's see. What's another good example of that? Okay, this one. Let's figure out how much work was involved in building the Great Pyramid of Giza. Remember we mentioned this a little while ago? Okay, I'm going to find out how much work it takes to build this thing. Now think about it. You're the master architect for Pharaoh, the living God. And the living God knows he's going to die in 20 years. You've got 20 years to build this frickin' thing because it's his tomb, right? If you're off by 1 day, it's not ready when he wants it, it's over. You want to know exactly, 1, how much work is involved in building this freaking thing. 2, how many people I need to get this done in 20 years. So the issue of manpower comes into play. How much work does can one person do in a career of 20 years? If you're, a master masonry person, whatever. Cut to the chase. Slave, okay? Did you ever watch the 10 Commandments? Right? With, what's his name as Moses? Charlton Heston as Moses, right? So shall it be written. So shall it be done. Right? With Yul Brynner as Ramses, the Pharaoh. You don't know this movie? No? You gotta see it. Anything with Charlton Heston in it, you gotta see it. Anything with Yul Brynner in it, you gotta see it. Anyway, so we digress. So we got to figure out the volume of the pyramid. We got to figure out the weight of the clay used to build all the bricks in the pyramid. We got to figure out the work done to lift all these bricks into place. Then we're going to have a humongous amount of Newton meters to do. Is this in Newton meters? Wait, look at it. No, this is in feet. This is going to be in foot pounds. I got units in feet and pounds. Yeah.
Are you going to do all that before the break?
And no, I'm just telling you what I'm going to do right after the break. I know, I'm getting there. All right, so that's the game plan right after break, okay? All right, we got to talk about how much one person can do, how much work one manpower is, okay? All right, so we'll take a break for 5 minutes. It's 8:15, so 8:20-ish. We'll be back, okay? All right, 5-minute break. Because it doesn't pause. I've tried that. It's foo-bars everything. Remember how easy it is to foo-bar stuff? And XP, it doesn't foo-bar. I've done it. But on here, I've played with it. Nah. So let's just leave it, okay? I don't know. I'm going to actually eventually do all this in Linux. Cause really? Is it really? Yeah? Oh, yeah? Okay, great.
I went back, and if I find it on the website, last night's video.
Yeah, I told you.
Well, no, you submit, no, I know the button, you know, the one that was saying
Yeah.
that, but the
Okay.
regular lectures, last one was lectures, which was 7:16.
Well, they're all on YouTube. Just look up Matt
No,
Calc
I'm talking about the songs.
Okay.
That you're recording.
Oh, they're all here. Let's see, I'm going to show us. Is this on here? Well, now, yeah.
Oh, it's fine. I will.
Whoops. Yeah, let's get rid of that. Okay. If you go to FTP, // and it takes a moment sometimes to wake up my little FTP server at school. Come on, wake up. Oh wait, I don't even have the internet on. All right, forget I did that. Okay, yeah, okay. I can't do it on here because I didn't set up the internet. But the problem with Internet Explorer is it doesn't display FTP sites too well. So when it comes up, you go to Page and open FTP site in Windows Explorer. Then you can see everything.
Oh, do that.
For some reason, some of the
I got
folders
that.
don't show up. Otherwise,
Should
when it pops up, then go to Page.
Where?
Right there, it's right in
Okay,
Internet
that's one.
Explorer.
I'm
Go to
sorry.
Page, go to Open FTP site. Yeah, I don't know why
Maybe
this
you'll forget to turn this off at 9 because I gotta go home and get on full blown. Thank you.
Okay,
I gotta get well for Friday.
all right, okay. All right, 5 minutes, here we go. That's a little more than 5 minutes. What was it, 8:20? 8:22, okay. All right, here we go. You ready? All right, I have to describe to you the dimensions of the Great Pyramid of Giza in Egypt. Okay? It's a square pyramid. What does that mean? The base is a square, right? If you talk about a prism where the bottom is a square and the top is a square, the volume is side times height, or length times width times height. It's just a box. But this is not. This is a pyramid. So it's the area of the square, goes to a point, times the height over 3, right? But wait. Let's talk about this. Well, I'm going to do the same kind of argument that we just did for pumping the oil. I'm going to make a similar argument for placing clay bricks. Again, if you watch Charlton Heston, you use your feet with the mud and the straw, you mix it all up, you make the clay, you dry it in the sun, it's a brick. We're not counting that part of the work. We're counting now, pick up the brick and take it into the rightful place in the pyramid and build the pyramid, right? So I'm just talking about the work of picking up the brick and putting it in the right place. Not making it, not transporting it from where you made it to where the pyramid is. Just we're at the base of the pyramid and we're going to pick up the brick and we're going to put it in place. Okay? All right, so consider the following pyramid. It looks like this. The base is a square. So there are 4 sides, all triangles. And they're all, I think, congruent triangles. Okay? The base of the square is 755 feet long. The height of the pyramid is 410 feet. This is not drawn to scale, obviously. Okay? All right, so it is reported that the Great Pyramid of Egypt, or of Giza actually, was built in 20 years. If the stone making up, well, it's clay, of the pyramid has a density of 200 pounds per cubic foot. So there's your density constant. 200 pounds per cubic foot. And we're assuming that the clay is made, the bricks are made of uniformly dense clay, and that's how dense it is. Okay? Find the total amount of work done by building the pyramid. The pyramid is 410 feet high, with a square base of 755 feet, and estimate how many workers you need to do this. Okay? All right, so we're going to do the exact same argument we did before. I'm going to slice this parallel to the base. I'm going to take a slice. But that slice is not going to be a cylinder, is it? What's it going to be? It's going to be like a box. It's going to have a square face, all right, and a certain thickness, all right? So if I call this, I don't know, delta H, this thickness, or delta Y if you like, whatever. How do you get the volume of that whole slice of clay, of brick? What's your delta V? Give me a Riemann statement for the volume of that slice. It's the area of the face times the thickness. How do you get the area of a square? Side squared. Okay, boom. That's your Riemann statement for the volume of that one slice. Now remember, we're going to do a Riemann statement for the volume, then based on that for the force, then based on that for the work, and then we're going to integrate that to get the total work done. Right? Just like last time. Okay, but what's S in terms of H? Let's say H is how high off the ground this slice is. Let's call this piece H. Okay? And this side, the side of the slice is S. How do you get S in terms of H so I can integrate later on? I only want one variable. I don't want 2 variables, right? So how do I get S in terms of H? Well, think of it. Let's look at this cross section. If you slice down the middle of this thing, that's the side of the square, slice. That's the side of the square base, right? The slice is H units from the ground, H feet from the ground, but this whole thing is 410 feet. Don't we have similar triangles again? Right? If this is parallel to this, then this transversal makes corresponding angles congruent. This transversal makes corresponding angles congruent. And they match, they overlap on this angle. So both triangles, let's say ABC, triangle ABC and triangle DBE have to be similar. So the sides are in proportion. So I'm going to say S is to 755. The base of the little triangle is the base of the big triangle. As the height of the little triangle is to the height of the big triangle. What's the height of the little triangle? No, that's this. This is 410, this is h. What's that? 410 minus h. So the height of the little triangle is 410 minus h. Let's write that. 410 minus h. The height of the little triangle to the height of the big triangle is 410 minus h to the height of the whole thing is 410. So I want to get s in terms of h. I get s alone simply by multiplying by 755. So s is 755 over 410 times 410 minus h. So delta V is s squared, which is that, squared, delta H. That's my delta V, my Riemann statement for the volume of one slice. Are you with me? Is that okay so far? We've done stuff with the similar triangles before, right? That's all that's going on. Now, how do I go from there to a delta F, right? Just like before, we had, where did we do it? We had a delta V, then we had a delta F, then we had a delta W, then we integrated to get W. What's your delta F? Well, what are the units of volume here? If you just made this into an integral, you would get a humongous number of whats? Give me units. Cows, moons, chickens, parsecs, angstroms, something. No? H is in what? Feet. This is in feet. I'm squaring feet. It's cubic feet, yes? What if I take cubic feet and multiply by pounds per cubic feet? What do you get? Pounds. Now notice this is different than before. We had cubic meters times kilograms per cubic meter gave me kilograms, not a unit of force. I had to multiply that by G. Here I have cubic feet times pounds per cubic feet gives me pounds. That's a unit of force. Remember, pounds is a unit of force. Slugs is a unit of mass. So it's a lot easier in the English system. Simply take this and multiply by what to get force? Take this and multiply by what to get the force? In pounds. By 200, that's it. All right, so delta F is just simply 200 times what we had. What the heck was it? Okay. 755 over 410 squared times 410 minus h squared, delta H. Now, I could stop here and actually figure out the volume if I wanted to in cubic feet. I could stop here and actually find the weight of the entire pyramid in pounds. If I make this into an integral, I could. But that wasn't my point. My point was to get the total work done, right? So how do you get from force to work? I know the total amount of force exerted by this one slice. In other words, the weight of that slice. How much work is involved in getting those bricks from the ground up? Remember, work is what times what? Force times distance. We have force if we integrate this. What's the distance? That force represents the weight of this slice. How far did I have to put it from the ground? H. Okay. So delta W is simply that. Whoops. Times H. Okay? So if I ask you for the total volume of brick, integrate this. If I want the total mass, not mass, sorry, weight of the pyramid, integrate this. V was in cubic feet, F is in pounds. But if I integrate this, what am I going to get? This is in pounds, and I'm multiplying by what? The only difference between this line and this line is this product. So this was pounds times feet. So what do you get? Foot-pounds, a unit of work. This is good. Let's see how many foot-pounds is involved in building this whole thing. Now remember, it's not one person working, and in other words, a whole ton of people are going to be working simultaneously over a period of 20 years. So this is doable. Okay, it was done. How do you get W? W is going to be what? Remember, this is the work done to place these bricks, the bricks that make up this slab, right? I want to add up all those slabs and get the work done for down here, up there, all of this stuff, right? So integrate from what to what? 0 to 410, that's in terms of age. So I'm going to take the constants out. They can go anywhere, inside or outside. I'll just put them out. Times the integral from 0 to 410 of 410 minus h quantity squared times h dh. There's the integral I want to do. How do you do it? How do you anti-differentiate the 410 minus h squared, h dh? Well, who's you then? Now it won't work, right? If u is the inner function, 410 minus h, du is simply dh. You don't get the h. You got to FOIL it out, I guess. All right, so let's FOIL it out. Okay, equals 200 times 755 over 410 squared times the integral from 0 to 410. I didn't integrate yet. I'm just trying to make it integrable. All right, it's going to be 410 squared, and then it's going to be negative 410h and another negative 410h, so minus 820h plus h squared times h. What happens if you take this times h? You got h all over the place. All right, let me write it that way. We'll put a little h here, h times h squared times h. That's doable. Is that terrible? What's the antiderivative of h dh? H squared over 2. What's the antiderivative of h squared dh? H cubed over 3. What's the antiderivative of h cubed dh? H to the 4th over 4, and so forth. Yeah. Do we really want to do all of that? How about we just start plugging this into Ziggy and see what we get? All right, so Ziggy, here we go. In fact, if I wasn't doing it by hand, I could just plug this into Ziggy. Let's plug this into Ziggy. This is trying to get it to do it by hand. I don't feel like doing it by hand. Okay, you could, I guess, if you wanted, but why? All right, so let's throw all this stuff into Ziggy. Let Ziggy do all the work. Second mode is quick. Clear all this stuff. All right, so it's 200 times 755 over 410. That quantity is squared. Times the integral, so math 9. Remember the numerical derivative is math 8. So math 9 of, and I'm not even going to FOIL it out. It's going to be quantity 410 minus, now it's in terms of h on the page, but, I'm in parametric mode. I'm just going to use this variable. It doesn't matter what it is. I'm t instead of h, big deal. So 410 minus t, quantity squared, times t with respect to t. Right? Instead of h, I have t. And there's your dh is your comma t, right? Okay, from 0 to 410, so comma, 0, comma, 410. All right, now did I do that all correct, Mike? Yeah, I don't know if it'll complain, but all right, let's see. Close it, see what we get. Okay, 1.597 times 10 to the 12th foot-pounds. Name that number. What's times 10 to the 12th mean? 10 to the 6th is million. 10 to the 9th is billion. 10 to the 12th? Trillion. We're talking about roughly 1.6 trillion foot-pounds of work. All right, let's get a little bit more precise here. How about we make mode float and do the calculation again. I just want more decimals. Oops. So there you go. All right, so is that 12? That's not 12 places, is it? Let's write this number down. It's approximately 1,597,020,042 stuff. I don't know what. Right? Is that 12 places? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I don't know what's here, but roughly, okay? To the nearest 1,000 is probably correct. All right, so that's how many foot-pounds we're talking about. Now the question is, how many people do you have to employ? They were slaves, so we didn't employ them, but house, to actually get this done in a reasonable amount of time, which happened to be 20 years. Well, there's more information. It says, archaeologists have figured out that every laborer worked 10 hours a day for 300 days a year for 20 years. And a typical worker lifted 10 50-pound blocks a distance of 4 feet every hour. That's a man-hour. 10 50-pound blocks, 4 feet in an hour. Let's talk about that. Okay, wait, I think I need another page. Hang on. Okay. A manpower, or laborer power, is 10 50-pound blocks moving 4 feet in an hour. All right? This is a unit of power because this is foot-pounds per hour. Okay? That's called a manpower. All right? So this is how many blocks he moved. This is the force of every block, the weight of every block. So technically, you're moving 500 pounds, 4 feet. So that's 2,000 foot-pounds per hour. That's what one person does, 2,000 foot-pounds every hour. But each person worked a 10-hour day for 300 days a year for 20 years. So how much work did one laborer do? 2,000 foot-pounds an hour, 10 hours, 300 days, 20 years. Just multiply all this stuff together. Okay? If I multiply this by hours, I get foot-pounds done in 10 hours. If I multiply that by days, I get foot-pounds done in 300 days. Multiply that by 20, I get foot-pounds done in 20 years. How much work one guy does in his entire 20-year career, let's say, right? So what is that? 2,000 times 10 is 20,000. 20,000 times 300 is 60,000, 6 million. Am I good? Times 20 is 120 million. So we're talking about 120 million foot-pounds in 20 years. So how many guys did you need? This is one guy. How many guys do you need to do this much work? Divide the amount of work you have to do by the amount of work one person does. That's how many people you need. So let's see. So let's take 120 million and divide it into that. Divide that answer by 120 million. Now you could write 120 million, or there's another way to write it. 20, and then second comma, million is 6. That's the same thing as 120 million. You could write it out with 6 zeros after the 120 if you want. Equals 13,308.5 people. All right, so what do you tell Pharaoh? You're the master architect, and you need to get this done in 20 years or else. So you tell Pharaoh says you can have whatever the hell you want. Do you tell Pharaoh that you want 13,308 people working for you for 20 years straight? Or 13,308.5 people? Half a person is dead. Sorry, no work. Or 13,309 people. Right. Play it safe. 13,310 people. Play, right? You probably fudged. 14,000 people. So give me 15,000 people, right? But technically, all you needed was 13,309 able-bodied workers working a 10-hour day, 300 days a year for 20 years straight, nonstop. You had to house these people. You had to feed these people. You had to take care of the medical needs. What if the block falls on his toe? Yeah. You need doctors. What if he broke his leg? You need another guy. Wait a minute. Each guy has a wife, and each wife has 3 kids. You're talking about a humongous town. 13,309 people and their families. Right? So what is that? At least 50,000 people. 100. You could get close to 100,000 people before you're done. Somewhere around 52,000 people, let's say, rough figures, 52,000 people. That's a big town. That's the nation of Israel, right? Let my people go. Those are the people that left. 50,000 people, or at least, maybe more, by the time Moses showed up, right? This is historical stuff. This is for real. So that's, historically speaking, architects have named this number. There were 13,309 laborers working on that one pyramid nonstop for 20 years. And the support system behind that a town, they had to build a town for these people to live in, All right, and granaries and latrines and, you get the idea, right? It's a big undertaking. But Pharaoh is God on earth, so hey, and you can do anything. So, any questions on work? That's all you need to know about work. That's a new application of integrals today. Yesterday was area, volume, arc length. Today was work. Okay? Now, tonight's homework for section 8.5, it says do the multiples of 5 on page 406. But let me amend that. Just do 5 and 15. 5 and 15 are related to work problems. 10 and 20 are not related to the kind of work problems we talked about today. So just do 5 and 15 for 8.5, or page 406. All right, so just do 5 and 15 for that homework, okay? 5 and 15. It says 5, 10, 15, 20. 10 and 20 have to do with water pressure under the ocean, blah, blah. I'm not going to get into that. But what we've done, you should be able to do 5 and 15, okay? Those are good questions. All right, so that's it. Up to here is what the test is on, including anything that happened the first 2 weeks could be on the test, right? What I'm doing from here on is not on the test. From now on. What we just did can be on the test. Yeah. All right, so we got to talk about what are sequences and what are series, because next week we're going to be talking about power series. Power series is a nice way of using the power rule to integrate anything. You can rewrite a function in terms of a power series. A power series, to integrate or differentiate it, only involves power rules. It's very easy to do, even if it's a very complicated function. So next week we're talking about power series. But before we can talk about power series, we have to know what a series is. And before we know what a series is, we have to know what a sequence is. Has anyone ever worked with series before? Series of constants, just adding up a bunch of numbers? All right, let's talk about this. Now, a sequence is a special kind of function. So we're switching gears, okay? Here we go. This is 9.1, 9.2. A sequence is something like this. Let me define the sequence A sub n to be, 1 over 2 to the n. What does that mean? That means you're going to plug in integers. Now, n is the variable you're plugging in stuff for, right? What's the domain for n? It's not what you would think. from in this unit, n is an integer. More likely, it's a natural number. Wake up. Okay? What's a natural number? Give me an example of an integer. How about an integer? Give me an example. Any integer. 2, what else? Another example. -2, -3, 3, 5, 10, a million, -2 million. It's any number it could have a positive or negative, but no decimal part, no fractional part, right? 1, 2, 3, -1, -2, -3, 0 even. All right, those are integers. If I say just whole numbers, what does that do for you? What's the difference between the set of all integers and the set of just whole numbers? Only positive and including 0. Think of whole as 0 as a whole, okay? Whole numbers include 0. So we're not talking about negatives. 0, 1, 2, 3. So usually the domain of a sequence is whole numbers. Unless it's not defined at 0, then it's natural numbers. What's natural numbers? The smallest whole number is 0. The smallest natural number is 1. Okay? So if I say natural numbers, we're talking about counting numbers. Cavemen counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? That's when you celebrated. That's why when you celebrated the end of the millennium, you screwed up. Right? You ever hear that Prince song, 1999, right? What's so great about 1999? New Year's at the end of 1999, boom, 2000, end of the millennium, right? Wrong. Because the ancients didn't know to count from 0. We do that in computer science, in computers and engineering. We count from 0. But the ancients started counting at 1. So the first decade after Christ started with year 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Year 10 was still part of decade 1. If you keep that up, year 100 is still part of century 1. If you keep that up, year 2000 is still part of millennium 2. You shouldn't have celebrated the end of the millennium at the end of 1999. You should have celebrated the end of the millennium at the end of 2000. 2001 was the first year of the third millennium. Did you know that? 2001 was the first year of the third millennium. Did you know that? See, you wasted the party. You had to do it again. Did you do it again? I did it twice. No? Oh well. So anyhow, so what does that mean? Either start at 0 or start at 1. Can you start with 0? Can you plug in 0 here? Is 1 over 2 to the 0 defined? Is that a real number? Yeah, okay. So the domain of a sequence is either whole numbers or natural numbers, depending on whether it's defined at 0 or not, okay? But notice what you get. I'm going to say start with n equals 0 and go to, say, infinity. This is an infinite set. If you plug in 0, what do you get? 1 over 2 to the 0 is 1 over 1 is 1. Now remember, I'm plugging in natural numbers or whole numbers. What's the next n? 0, then 1, then 2, then 3. All right, plug in 1, you get 1/2. Plug in 2, you get 1/4. Plug in 3, you get, what's 1 over 2 cubed? 1 over 8, and so forth. This is an infinite sequence. You could talk about a finite sequence. You could say, okay, let a sub n start at, say it's 1 over 2 to the n again, but start at n equals 2 and stop at n equals 4. Then what do you get? If you plug in 2, what do you get? 1 over 4. Plug in 3, you get 1 over 8. Plug in 4, you get 1 over 16. So this is a finite set. This is an infinite set. So what's happening here? We have a new kind of function. We call it discrete, not continuous. Discrete. Continuous functions, the y values, you plug in all the x values, all your y values, and they all touch. They're all continuous. They make a curve. You just, right? There's no gaps. Here there's gaps. If I graph this for n equals 0, I graph 1. For n equals 1, I graph 1/2. For n equals 2, I graph 1/4. For n equals 3, I graph 1/8. It's points. It's just points. It's not a curve. So this is a discrete function. You don't get a continuous function of points all touching, connecting. You get a bunch of discrete points, separate points. How do you graph this? We could do it on the calculator. Yeah. Well, you could do that, but there's an actual sequence mode on here. Go to the TID3 and go into mode and change it from function mode to sequence mode. Now if you go into y equals, you can graph sequences. Now I called it a sub n, they're calling it u sub n. Big difference. Okay? What's u sub n? In this case, it's 1 divided by 2 to the, now notice if you hit the x key, you get the n key instead. Okay? Actually, it's not n, it's nu, the Greek letter nu, whatever. All right, now if you're graphing this, you have to tell it where to start. Where did I start? At n equals 0, right? So is that right? No. So the first n value I'm plugging in is 0. I better say so. All right, now let's take a look at the window. Let's say I want to graph the first 10 elements from 0 to, well, 0 to 10. Is that 10 elements? Is that 10 points? Remember, we're modern. We're not ancient, right? We know how to count from 0. From 0 to 10 is really 11 numbers. If you count from 1 to 10, it's 10 numbers. But if you count from 0, there's another number, right? All right, so let's say I graph the first 11 members of this set. Don't worry about this, don't worry about this. I like xmin and xmax to match nmin and nmax, so I'm going to change that. It makes it easier to graph. So 0 to 10. So x is like n. What about the y's? Well, are those good y values? Look at the y values you're supposed to get. 1, 0.5, 0.25, 0.125. Is that in this y min, y max? Yeah, all right, that's a good. All right, so let's graph it. And notice what you got. Point, point, point. It's hard to see. Okay, let's change the window a little bit. How about if I blow up the y's a little bit? I don't need negative y's, so I'm going to start with 0. And the biggest y I had was 1. And how about a scale of 0.1 then? Blow it up a little bit, make it easier to see. Regraph. There you go. Now if you hit trace, when n was 0, you got 1. It should be there. No, go away. When n was 2, you get a half. When n is 3, you get a third. When n is 4, you get a quarter. Let's see if that's right. Trace. It starts with n min, and the first value is 1. Where it says y equals, that's the sequence value, 1. If you trace it, you get 0.5. 0.25, 1 quarter, 0.125, 1/8, 0.0625, 1/16, 0.0325, 1/32, and so forth. Okay. These values are getting closer and closer to what? 0, the x-axis. Okay, so if you have an infinite sequence, you can talk about the limit. The limit of the sequence is 0. All right, the limit, as n goes to infinity, of a sub n, the limiting quantity is 0. The last term is 0, or it gets closer and closer to 0. We're going to talk about convergence and limits of sequences, convergence and limits of series. Okay, we're going to talk about both. Now, that's a sequence. What's the difference between a sequence and a series? A sequence could be a finite set of numbers or an infinite set of numbers. But the series based on the sequence is simply what? The sum of all those numbers. Now, if I add a finite number of sequence terms, I'm going to get a number. But if I add an infinite number of sequence terms, do I get a number? Or do I get infinity? What do I get? Let me give you a hint. Do you ever hear Zeno's paradox? Zeno was a Greek philosopher that lived, I don't know, something like 5,000 years ago. And he said that motion is impossible. This was his reasoning. He came up with this sequence, except he started with n equals 1. Okay? If you start with n equals 1, the first value is a half, okay? And this is what he said, okay? Now, you're not going to hear me for a minute. Let's say you're an archer, right? I might actually be over here. You're an archer, you got a target over here, and you're standing over here, right? And you loose the arrow. What's the arrow going to do? It's got to get halfway there, somewhere along the line. It's got to get halfway there, right? This is Zeno talking. All right, from here to there, it's got to get halfway there, right? So what do? I walk the half, and I walk the quarter, right? of the total distance. And then from here to here, it's got to do another half. It's got to do an eighth of the total distance. Then you got to do a half. It's got to do a 16th of the total distance. That's the sequencing program. He's saying that you never get there because there's only a half, you never gonna get there. Well, of course, Zeno, 5,000 years ago, didn't know the concept of limit. In the limit, this sum is 1. You get the total distance. 1/2 of the distance plus 1/4 of the distance plus 1/8. Eventually, you get the total 100% of the distance. How do you see that? Well, let's graph this out too. There's a way to graph series on here, even though there's no series mode on here, notice. So if we're talking about Zeno's paradox, we're talking about the sequence that goes from n equals 1 to infinity. So you get 1/2, 1/4, 1/8, 1/16, and so forth, right? Forever. The series is the sum of all those values from n equals 1 to infinity. That's going to be 1/2 plus 1/4 plus 1/8 plus 1/16 plus. What is that sum? Let's find out on the calculator. This is how you do it. Now notice there's no sequence mode on the calculator, but we can fool Ziggy into graphing pieces of the sequence. This is what I'm going to do. I'm going to tell it to graph 1/2. Then I'm going to tell it to graph 1/2 plus 1/4. Then I'm going to tell it to graph 1/2 plus 1/4 plus 1/8. Then I'm going to tell it to graph 1/2 plus 1/4 plus 1/8 plus 1/16. What I'm ending up doing is I'm graphing a sequence of partial sums. The first one, the first two, the first three, the first four, the first five, the first six, right? I'm going to graph those numbers as dots, as sequences. If the limit exists, if the series exists, if that sum exists, adding up infinitely many numbers, which intuitively makes no sense, right? Add up infinitely many numbers, you should get infinity, right? Not always. If the limit exists, the sequence will go to a horizontal asymptote because the last term of the sequence, the limit of the sequence of the partial sums, is the last term is the sum of all of them. The first term is the first one. The second term is the sum of the first two. The third term is the sum of the first three. The fourth term is the sum of the first four terms. The last term is the sum of all of them. If that number exists, if that point doesn't go off to infinity, I've got a limit, the series exists. How do you graph that sequence of partial sums? Okay, this is what you do. You go into your sequence that you wrote in y equals, okay? And before this, what you're adding up, you're going to add one other little thing. Okay, let's see. Do a second insert because it's usually in overwrite mode. And you're going to use second 7, open parentheses, of n minus 1, close parentheses, plus. Now, does that look familiar? Isn't that the notation we use for Newton's method? Right? X sub n was x sub n minus 1 minus f of x sub n minus 1 over f prime of x sub n minus 1. The same kind of notation. What does this mean? Well, you still have to tell it where to start. Am I starting at 0? What was the first term of Newton's paradox? Was it 1? No, it was 1/2. So I got to start at, what's n? If my first value is 1/2, what's n? It's 1. Okay, so I got to fix that. Just put a 1 there. So notice what this is doing. It's saying take all the values you've had so far, get a new value of n, get the new sequence value and add it on and plot that. If you do that, you have to say what's the first value. It doesn't know how to get the first one. It has to have the first one to get to add on the second one, add on the third one. Right? It doesn't know where to start. So I'm starting at n equals 1, and at n equals 1, the first term of Zeno's sequence was what? 1/2. So write 1/2. Okay? And if you graph that, and you get a horizontal asymptote, then the limit of the sequence of the partial sums exists, which means the series exists, the sum of the whole thing. So, okay, let's see if there's a good window. Graph. All right, so remember, it started at n equals 1, and the first term was 1/2. Then it goes to n equals 2, and it takes 1/2 plus 1/4. That should be 3/4, right? Let's see, let's trace this. Is that right? Starts at 1/2, then it's 3/4. 1/2 plus a quarter. Then it's going to be 1/2 plus a quarter plus an eighth. Well, you could check that that's 7/8. It is. And so forth. But wait, it's going way off the screen. If the limit exists, what did we say it was? We said it should be 100%, 1. Okay, so my window isn't good. My Y max isn't good. It's hard to see it. So let's make a Y max of 2, let's say. So I can see whether it goes to 1 or not. It's hard to see. Graph. You see it's going to horizontal asymptote? Halfway from 0, Y min is 0 to Y max is 2. It's looking like it's going to 1. It's not that obvious. Now, be careful. If you make N max and X max big enough, these dots get so close together as to look like a curve that's continuous. All the points are touching. That's not what's happening, but I'm going to blow it up. Are you ready? Window. Instead of the first 10, let's do the first, I don't know, 20. I like to make N max and X max match. Makes life easy. Okay, regraph. So now it fit 20 dots on the same screen, so they're getting squished together, right? Does it look like it's going to a horizontal asymptote? Does it look like it's going to 1? Because that's 2, right? Let's do it again. Window. How about we make it the first 50? And 50 is big enough, I'm going to get an X scale of 10 with the hang. Now remember, they're not touching. This is not a continuous curve. This is a discrete function. A bunch of dots. Do you see how it's nice and flat? That means that the limit of the sequence of partial sums exists. That limit, the last term, is the sum of the entire sequence. So the series exists. What is it? Well, let's do a convergence table. Second mode is quit. I'm going to actually do a convergence table on alpha U1. Remember y equals? We were in U. Oh, sorry, this is not U1. It's just U. It's just U. Sorry. I'm thinking of the 89 that has a U1. So it's just U. Okay. Blah, 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 blah. Okay, I want U of 1. We knew that. I want, let's see, second enter, U of 10. Remember, I changed it from fixed 4 to float, which is, in this case, like fixed 12. Okay. I want U of 100. Now this convergence table might take forever because I have so many decimals. It's really easy to do in fixed 4. Do you see it's going to 1. Okay, and how about U of 1,000? So it generates 1,000 terms, adds them all up, and you get, hopefully 1, right? Because didn't we say Zeno's paradox said it should be 1? It overflows? Because the denominators get so big so fast, the powers of 2, yeah, it's probably going to crash. Okay, so quit that. All right, let's do it this way. How about mode? Change it back to fixed 4. It'd be easier to converge to 4 places. All right, second quit that. Try it again. Let's show the convergence table. All right, so, whoops, where's my delete? U of 1, U of 10, U of 100, rounding off to 4 places, right? I did a fixed 4 in this. Yeah, I still can't do the 1,000, can I? All right, maybe I can do this. How about, it's hard to see, it converges, but it converges very slowly, so the calculator may not be able to do it. Let's do, all right, how about this? U of 10. No, that's not 10. Dang it. Hang on. U of 10. U of 20. U of 30. Actually converges very fast if this works. Okay, there you go. So there's a nice little convergence table of 4 places, all right? So yeah, that limit exists. So what is the sum? It equals 1.000 approximately. Because we did fixed 4, so we're only sure about the first 3 decimal places, right? So I'm going to say it's approximately 1. But we can prove later on, we're going to prove later on that this is exactly 1, in fact. Okay. So that's a sequence, all those terms. That's a series, the sum of those terms. You can have a finite sequence or an infinite sequence. You can have a finite series or an infinite series. What's weird is that infinite series sometimes add up to a nice real number. Okay. Alrighty. All right, how about if we do a finite sequence? Here's another one. Let's say b sub n is 2 to the n. Okay. And n starts at 1. Nah, that's 0. What do you get? If you plug in 0, what's the first number? Plug in 1. 2 to the 1 is 2. Plug in 2. 2 to the 2. 4, 8, 16, 32, and so forth. Okay? All right, this is known as the Caliph of Baghdad sequence. Are you ready? You live in ancient Baghdad, and the Caliph has gazillions of drachma. And you're a poor beggar in the street. You ever watch like Aladdin, that cartoon movie? Right? You're like Aladdin, you're a beggar in the street. You need a job. Freaking Caliph of Baghdad, he's got a gazillion drachmas. He can pay me something. So you go over to the Caliph and say, look, give me a job. He says, okay, sure. You can muck out the horses' stalls. I'll give you 1 drachma a day. It's like, great, at least I don't starve. 1 drachma a day. So you're doing this for a while. It's like, 1 drachma a day? Geez, that's not a hell of a lot. I'm still starving over here. So you go to the Caliph and you say, look, I need a raise. How about, give me 1 drachma today, 2 drachma tomorrow, 4 drachma the next day, 8 drachma. You got a lot of drachma. A drachma is like a penny. I mean, come on. Oh, you can spare it, right? Okay, fine, sure. All right, this is a finite sequence. You got this job for a month, 30 days. My question to you is, how much money did you make? Okay, let's say you take every drachma and you save it in the Bank of Baghdad. Okay, how much money do you got? Is it a lot? Let's modernize this. Let's say these are pennies. How many dollars do you have at the end of the month? How many dollars have you earned at the end of the month? Now, if you just did 1 a month, 1 a day for 30 days, you got 30 pennies. Wow. What is this finite series? What is the sum? Actually, I'm not going to infinity. I'm going to 30, okay? All right, so notice, from n equals 0 to n equals 30 is how many days? 31. So it's a 31-day month, let's say, okay? So up to, I'm going to stop. It's a finite sequence, okay? I'm going to stop at 2 to the 30, whatever that is. That's a pretty big number, isn't it? 2 to the 30? How much money is that? That's your last paycheck. What if you add them all up? How much money you got? Well, let's graph this thing. I want the series, as n goes from 0 to 30, of 2 to the n. I want 1 plus 2 plus 4 plus 8 plus up to 2 to the 30th. How much money is that? Let's say that's pennies. Make it easy. Okay? Well, let's ask Ziggy. First of all, what is 2 to the 30th? Your last paycheck. It's that. Okay, name that number. You ever hear that show, Name That Tune? You ever see that show? You compete against other people, and you can only get a certain number of notes, the first 4 notes of the song, the first 3 notes, whatever. And if you get it with less notes than the other guy, you win. And you get $1 million. It's like $1 Million Password. You ever see that? Right? Well, they used to have a Name That Tune. Name that number. What the heck number is that? Is it 10 billion? Is it 1 trillion? What the freak is it? Is it trillion? Let's see. Let's see. 3. Yeah. So hundreds, thousands, millions, billions. So it's 1,073,741,824 pennies. How many dollars is that? Divide by 100. All right. So divided by 100 is my last paycheck. This is just my last paycheck, not all the money I made. Is, well, if it was in billions now, it's 10 millions, is it? Yeah, $10,737,000, $418.24. Okay, yeah. No, because I'm doing all 31 days. Subtract 1 from what? Why? Well, you're talking about powers, you're talking about binary or something, right? How to convert from binary to decimal. Is this computer science? What you talking about? No. No, I'm saying physically your last paycheck is 2 to the 30th. Pennies, that's it. That's what you got. I'm the caliph. I can make it whatever the freak I want, okay? That's what it is. No, there's no minus. I don't get where the -1 comes from. But all right, let's stick with it, okay? Okay, so let's graph this thing. Let's see how much money we make every single day. Let's graph it as a sequence. And then we'll add it all up. Okay. So go into y equals. And I'm not adding everything up yet, so just clear this line. All right, let's start here. Is my n min 1? Is n min 1? No. So it's what? It's 0. Okay. And what am I adding up? It was 2 to the n, right? So 2 to the n. Now, if you're not adding up all the terms, you really don't need this. It'll ignore this, but I'm going to clear it out. I just want to graph this much. Okay? What's a good window? N min was 0. N max was 30, right? It's only 31 days. Don't worry about this. Don't worry about this. I'm going to match this. It makes life easy to read the graph. Okay. What about Y min and Y max? What do you think it's going to be? Y min could be 0. You're not going to have negative pennies, right? Y max? It was that billion something, right? I'm going to put in 2 billion just for the hell of it. Or how about, yeah, all right, 2 billion. I think that's 2 billion. I don't know. Should be 12. I think I messed up. Yeah. Whoa. What did I do? Got it. Don't do that. Don't do that. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, it is 9. Yeah, it's 2 billion. That's right. And so if you want a nice scale, how about 200 million? So 8 zeros. Or actually, let's make it 1. 100 million. Okay? So let's graph that. There you go. So if you trace it, you get 1 penny the first day, 2 pennies, 4 pennies, 8 pennies. Right? The fourth day, because remember we started at n equals 0, so n equals 3 is the fourth day. And 16 pennies, 32 pennies, and so forth, right? Finally, you get about $1. Thank God, after 8 days. Okay. $2, $5, $10, $20. On the 13th day, $40, $41 almost, right? On the 20th day, what the hell is that? $10,485,000, 76 cents, and so forth. Do I get N max here? Do I get the 30? There it is. 28, 29, 30. That's it. Okay. So that's at 1 billion some odd pennies. Okay. All right. So how do you add them all up? How big is the sum of all those numbers? Is it in the range of a billion, a trillion? What is it? I don't know. Let's find out. Go into y equals and make Ziggy do the sum. How do you do that? You change this line by adding what? U sub n minus 1 plus whatever it is, right? So second delete is insert because you don't want to write over what you had. And it's second 7 is u, open parentheses, and technically it's nu minus 1, close parentheses, plus. But then you have to say what the first paycheck was. What is it? Because it doesn't know how to get the first one. It knows how to add on, right? So it was 1, wasn't it? And then when we graph that, let's see how big this gets. All right, trace that. $1, $3, because 1 plus 2. 1 plus 2 plus 3. I'm sorry, 1 plus 2 plus 4. $7. 1 plus 2 plus 4 plus 8, $15, or 15 pennies, whatever, right? 1 plus 2 plus 4 plus 8 plus 16 is 31 pennies. Okay, let's see what the last one is. 24, 25, 27, 28, 29 is off the 29 is on the screen. 30 is off the screen, but there it is. It's 2 point something times 10 to the 9th. So it's over 2 billion pennies, right? If I do that on the home screen, second quit, I could do second U of 30. And the sum is that 2 billion? Yeah, 2,147,483. Wait, I said it wrong. 2,147,483,647 pennies divided by 100. You cost the Caliph in your first month of employ. What is it? $21,474,836 and 47 cents. Yeah. What? No. Oh, to the 31. Yeah. Okay. Okay. Yeah. Okay. Yeah, that's the sum. Right. Okay. But that has to do with binary code. I'm not going to get into that. That's a fluke because it's powers of 2. And when you sum powers of 2, you're doing base 2 numbers. Let me not go into that right now. Yeah. That's a pattern that only works in powers of 2. Okay. Yeah. All right. So we're about out of time. So guess what we did? We did 9-1. We didn't do 9-2. So that's tomorrow. Okay. Tomorrow we'll do 9-2, 9-3, 9-4. So don't worry about 9-2 for the homework. So 8-5 for the homework, 9-1 for the homework. And 8-5 was only 5 and 15, remember. Okay? All right, that's it for today. We're done. Huh, what? Yeah, what about it? No, actually.
You get, it's like a website where you get a penny, like